Hello everyone.
I'm recording the lecture for the class on 27th January because I have some other commitment during that time. So I'll record this lecture so that you can follow it up. We will continue our discussion on processes. A quick recap of what we have discussed till now. So we have discussed what a process is and how a process looks like in memory. So if you remember, we talked about several segments like code segment, text segment, or okay, the text segment contains the code, then the data segment, the heap, the stack segment, and so on. So that is how a process looks like in memory. So every process has this kind of an entry in memory. Also, we talked about something called a process control block, a PCB in short. So a PCB is a data structure which a kernel uses to keep track of different processes. So essentially PCB is part of the kernel. I mean, it is used. There is a PCB for every process, and these PCBs are used by the kernel to do the allocation between processes, keep track of which process is in which state, and so on. Right? And we also discussed process states. So we understood that processes are initially in the new state, then they become ready, then one is allocated the CPU, by which the state of this process changes to running. Then again, the process has to wait for some IO event or something by which its state becomes waiting and so on. So we discussed a whole process transition diagram, or I should say a straight transition diagram for processes, right, which was like an automata. And then we discussed how exactly context switch happens. So this is what we have discussed last week. Now let us proceed in our discussion on processes because there is a lot more to discuss. Let us begin discussing processing queues, which are essentially used for scheduling. Now we will study scheduling algorithms in detail later, but before that, we just want to talk a bit about process queues. So there are several scheduling queues which exist in the operating system. And a particular PCB for a particular process is linked to one of the queues at any given point of time. Okay, sorry about a typo here. I wanted to write a PCB is linked to one of the queues at any given point of time. Okay. And so there are several such queues and a PCB is linked to one of the queues at one point. At some other point, it may be linked to some other queue and so on. Right. So for example, we will see that there is a ready queue. So this queue contains all processes which are ready. Also, there is another queue, let's say, which is for processes waiting for a particular device. So if a process was ready or if a process was waiting for a device for some operation to complete on a device, say when that operation does complete, then the process is shifted from the waiting queue to the ready queue. Right, so processes can be or PCBs can be shifted from one queue to another by the OS. So a particular PCB is linked to one of the queues at any given point of time. And the PCBs in a queue are connected as a linked list. We will discuss more on this, a bit more on this soon. So essentially, what are these queues? Now, there are many queues in an operating system. So for example, each IO device has its own device queue. And this queue contains PCBs of those processes which are waiting for some operation on this device. Okay, so this is a device specific queue. Similarly, each event also has its own queue, which contains PCBs of those processes which are waiting for this event. What can be such events? We will discuss today. For example, one event can be that some other processes are waiting for a particular process to complete. Okay, some other processes are waiting for a particular process to complete. So completion of this process is an event. So you might say that all those processes are waiting for this particular event, that is termination of this particular process. Similarly, there can be different types of other events and processes can wait for those events. Now, as I said, there are several queues. There are several such queues, and PCBs or processes, you might say, are shifted from one queue to another depending on which state they are in. So process scheduling can even be represented as a queuing diagram. Right. So let's understand these things in a bit more detail now. So this picture you have seen, this is actually a part of the process state diagram which we discussed. The actually process state transition diagram is more complex. If you remember, there were other states like swapped in, swapped out, etc. We are not showing those here. So this is a smaller version or a simpler version of the process state diagram that we have discussed. Now, as the process goes from one state to another, it may be shifted from one queue to another. For example, there is something called a job queue, which contains all the processes which are currently there in the system. So when a process has just been added, that means it is in a new state, then this process is in the job queue. Okay. And after some time, maybe this process becomes ready, right? So ready to be allocated to the CPU. At that point, the kernel brings this process from the job queue to the ready queue. Some part of the kernel does that. Remember, PCBs are handled by the kernel. So PCBs are not handled by the individual processes. Rather, PCBs are handled by the kernel. So who brings a PCB from one queue to another? It's usually some routine in the kernel. Okay, so to continue our discussion. So initially the process was in the job queue. When it became ready, it was transferred to the ready queue. Now the scheduler or the process scheduler will actually look at this ready queue and it will select a process from the ready queue for execution on the CPU. How exactly is this done? So suppose there are 100 processes waiting in the ready queue. How will the scheduler select one process? This is called a scheduling algorithm, which we will discuss in a couple of days. But for now, understand that using some scheduling algorithm, the scheduler will select one of the processes in the ready queue. Then the actual task of allocating the CPU to that selected process is done by a dispatcher. Right? So dispatcher is the kernel process that assigns the CPU to a process selected by the scheduler. So basically, scheduler looks at the ready queue and selects one process using some scheduling algorithm, which we will discuss. Then the dispatcher allocates the CPU to this selected process. And we have discussed in some small detail about what a dispatcher can do. So for example, it has to repopulate the CPU registers with the saved state of this process. Right, these things we have discussed. So that is kind of gives an idea of what dispatcher does. And what scheduler does exactly? So I've told you what scheduler does. Basically, it selects a process from the ready queue for execution on the CPU. But how exactly does it select a process? This we will have a detailed discussion in about a couple of days, I think, when we discuss scheduling algorithms. Okay, coming back to our discussion on queues. So we have discussed about job queue and ready queue. Also, if you think that suppose a process is running, now it makes an IO request. So it is transferred to the waiting state. This we discussed. And as the process is transferred to the waiting state, possibly it is put in a device queue. Right, so now it is no longer in the ready queue because it is no longer ready, right? It is waiting for this IO to complete. That means it is waiting for this device on which it has made the request. So the PCB of this process is now moved to the device queue. Again, when the IO or event completes at some later point of time, the kernel will shift this PCB from the device queue to the ready queue, because presumably again, once the IO completes, again the process would be ready to be allocated to a processor. Therefore, it's shifted from the device queue to the ready queue. Great. So you see that processing, okay. What I want to say is the different stages in the lifetime of a process, right from new to terminated. The different stages in the lifetime of a process can be described using a process state diagram that we have discussed already, part of which you are seeing here. Another alternative is to describe this transition of a process from different states to different states. Another way to describe this is through a queuing diagram, which shows from which queue to which other queue a process is being taken. So to understand that, let us first just very briefly understand what kind of queues we are talking about. So this slide, partly the top part of this slide we have seen earlier. So in the last week we said that there is a C structure called task struct, which is used by the kernel to store the PCB of a process. So this structure has fields like the process ID, the state of the process, then many other different things which would possibly make more sense as we go ahead in today's lecture. Things like parent, children, etc. Then you see open files. So your process may already have opened a few files. That should be remembered. So all these things are stored by the kernel in the PCB. And if we talk in terms of the data structure, there is a C structure called task struct, which contains the PCB of our process. Now, when we are talking about things like ready queue, device queue, essentially these are doubly linked lists of this structure. Okay. So each node is of this structure type, task struct, and there is a doubly linked list, which I'm sure you have. So you understand how a doubly linked list works. So for example, this picture I think tries to show a ready queue. So here it is shown as a doubly linked list. Every node is a PCB. And there is this specific pointer called current, which keeps track of which process is currently running. This is just a representative picture. A ready queue need not always look like this, but in general, I hope you get the idea that this is how the operating system maintains these queues called job queue, ready queue, device queue, etc. In some form, PCBs are the nodes of the queue, and the queues are mostly or most commonly represented as doubly linked lists. So now that we understand a bit more what is a queue, so let me show you this diagram. Okay, before that, so essentially, as I said, there can be several queues in this operating system, one for each device, you see. So for example, in this, so by the way, these pictures are taken from Galvin and they are representative pictures, right? So it's not necessary that exactly what is shown here, those variables are being used by every kernel and so on. Like, I don't know if really every kernel uses variables like head, tail, etc. So don't take these, these names, etc., which are appearing here, don't take them too sacrosanctly. But these pictures are representative to give you an idea of how logically such queues look like. So for example, this picture here shows the ready queue, right? So you have every node is a PCB. So PCB of process 7, PCB of process 2, right? So this is the ready queue. All these processes are ready. So the scheduler, if you remember, should actually look at these processes which are in the ready queue and select one of them using some algorithm. So this is a pictorial representation of the ready queue. Similarly, there can be many other such queues. So for example, what this picture shows is one queue for every device. So let's say the system has two magnetic tapes. It's magnetic tape unit 0 and magnetic tape unit 1. These are its queues. Currently, no process is waiting for these magnetic tapes. I should say no process is waiting for any I/O operation on those magnetic tapes. Similarly, this is the queue for disk. The device is a device queue for disk, and 3 processes are currently waiting for some IO with the disk. So these processes either want to read from the disk or write to the disk. Okay, and that is why they are not in the ready queue. Right? Processes 3, 14, and 6, they are not in the ready queue because they are waiting for some IO operation on the disk. Similarly, there is a terminal, and process 5 seems to be waiting for some IO with the terminal. So this is how, like, there are several queues in an operating system, and a particular PCB can be in one queue at a particular point of time. Let's say PCB 3 currently it is in the device queue of disk. Now once the IO with the disk completes for PCB 3, it will probably be shifted to the ready queue, unless it is not waiting for anything else. Now this was a very high level definition, high level picture of queues. Also, let me show one picture more, which is this. I was telling a few minutes back that how the state of a process changes from its start till its termination can be represented in different ways. One way we have discussed earlier, which is the process state transition diagram. There we talked about ready queue, there we talked about the states like new, ready, waiting, running, etc. Right? So if I just go back, this picture, yes, like new, ready, waiting, running, etc. But you see that often, mostly, I should not say every time, but mostly there is a queue associated with different states. Like all processes which are ready are in the ready queue. All processes which are waiting for a particular device or waiting for IO with a particular device are waiting in a device queue. So since many of these states are associated with a queue, we can also describe very similar information using a queuing diagram. So that is what I am showing now. This one. This is a representation of process scheduling using a queuing diagram. Let me just walk you through what is happening here. It's nothing new. We have discussed this. Suppose this is the ready queue. So one of the processes will be allocated the CPU. Right? And once it is allocated the CPU, it can either complete and be terminated, or one of these events happen. This process can make an IO request. If so, then it is placed in an IO queue. So IO queue for this particular device, that device for which it has raised an IO request. Once that IO is completed, it will again be pushed back to the ready queue. Similarly, in another situation, when the process is running on the CPU, its time slice may expire. We have discussed this. There is something called a timer which the CPU sets, and that timer is decremented by the physical clock. When that timer interrupts, the kernel again is allocated the CPU, and the kernel understands that this process has run for one time slice. Now it should be put again in the ready queue so that some other process can get its turn to run on the CPU. Similarly, other things can happen. A particular process can fork a child and wait for that child to complete execution. This part we will talk in more detail today itself. Similarly, a process which is running on the CPU can wait for an interrupt. And so it's again, so this is an event, right? These two are events. These two are examples of a process waiting for an event. So in this case, this fork a child example, a process has created a new process called the child process, and it is waiting for that child process to complete or terminate. So it is waiting for an event. Similarly, in this last example here, the process is waiting for an interrupt to come. So again, it is waiting for an event. So it is no longer in the ready queue because it is waiting for an interrupt or waiting for an event. When that event happens or when that interrupt occurs, this process will again be pushed to the ready queue. So this picture also gives an equivalent way of representing how processes shift from one queue to another, or you might say how processes are scheduled, or how processes shift from one state to another. So we have essentially discussed the lifetime of a process using two different representations. One is the process state transition diagram, which we discussed in detail last week. And another one is this kind of a queuing diagram, which shows how a process moves from one queue to another throughout its lifetime. So both these are kind of equivalent. So one is giving particular states, names of different states in which a process is, like ready, running, waiting. The other is kind of more of a data structure based approach, where it is showing that in which data structure is the kernel storing the PCB of a process at a particular point of time. So at a particular point of time, the kernel may store the PCB of a process in the ready queue. At some other time, this PCB of the same process can actually go to a device queue, because at that point this process is waiting for an operation on that device. Again, when that operation completes, again the PCB can be brought to the ready queue. Right, so this representation is more from a data structure level, at which data structure the kernel is using to store the PCBs. So this was till now we have been discussing about process queues. Now we will talk about operations on processes. Since this is a recorded lecture, so I'm just proceeding without much of a break. But then please go through this recording, and if you have any questions, we will give you time to discuss this in the next live class, which will be on Thursday. Okay, let us understand a bit about operations on processes. So we will discuss about several operations that can be done with a process. Let us begin with the very first process, you might think, or first operation that a process needs. First, a process has to be created. So let us discuss process creation. Now, first of all, who can create a process? The answer is another process. Okay. So usually every process except one is created by some other process. Why am I saying except one? I'll soon come to it. Usually you can think that processes are created by other processes. So during execution, a process may create several new processes. And we use two terminologies which I want to introduce: a parent process and a child process. So the process that creates a new process is called a parent process, and the new process that is created is called a child process. Right. So a parent creates a child, and we will often refer to them as just parent or child, because hopefully the context is clear. When we parent, we mean the parent process which was running and which has created a new process. And when we say child, we mean that newly created process. Now understand that this child-parent relationship can be, I mean, it's not that a child process can never become a parent. Oh, so again, these terminologies are inspired by what happens in real life. So a parent gives birth to a child, that child also grows up, etc. And that child later, when he also becomes, or he or she becomes an adult, can give birth to other children. So here also, a parent process can create a child process. In turn, these child processes can create other processes. Right? So these children processes can become parents later, so that they can create other processes. Right? So in all, you might think of a tree of processes. Let's say process 1 creates 2 children, process 2 and process 3. And process 2 creates 3 more children, 4, 5, 6. Process 3 creates 2 more children, 7, 8, and so on. So there can be a tree of processes. If you can conceptualize an n-ary tree kind of thing. Let's say, for simplicity, if every process creates 2 children, then this will be similar to a binary tree. Okay. So understand that this child process is not, child process is just said to be at that point when this process is being created newly. Later on, this child process can become a parent also and create other processes. Now, one important thing to remember is each process has a unique identifier, which is called a PID, a process identifier. Now, this statement is important. So how to create a process? There's a system called fork, which we will study just now in detail. So the fork system call is used to create a process. Now, there is one special process in a Unix or Linux based system, which is the very first process which is created. Now, as I said, you might assume that every process is created by some other process. There should be one process which is the first process. So that is called init. Now, further discussion about init is out of scope of this lecture at least. Maybe we can come back to it later at some point of time. But I would invite you to know more about init. So look up some web pages or etc. There is this special process called init. We will talk a bit more about init later also at different points of time. But I leave it as a task to know a bit more about init process. So the init is the very first process, which kind of how it is created. For that I'm saying, so that will take us into details like how a machine boots up and how the OS actually starts. Right. So remember, the OS has to have, the OS uses several data structures. So somewhere those data structures must be initialized, must be dynamically allocated, and so on. So that is how a kernel starts up. Right. So if you are interested, please look that up and try to know a bit more about this init process. So for now, we are not discussing the init process. Rather, we will discuss the fork system call, which is used to create all other processes. Now, what happens when a fork system call is done? We'll see. So you see, the fork system call creates a new process. When this happens, so when a parent creates a child, initially the child is an exact duplicate of the parent. Please remember that a parent has an entry in the memory. We discussed that. Code segment, data segment, stack, heap, right? We discussed these things. The child will also have a duplicate entry in the memory, which is a very exact duplicate of its parent's address space. So right now, right after creation of a child, there is no difference between a child and a process, except for one. The process ID is different. Okay. So child and parent are two different processes. So the process ID is different. But apart from that, the child is an exact duplicate of the parent. It is executing the same instructions. It has the same data. It has the same open files and so on. However, later the child can have a different program loaded into it. We will see examples. This part, loading a different program onto the child, is done by the exec system call. Right, so this exec system call is used to replace a processor's memory with new programs or new codes. Okay. I think this slide may not be fully clear yet, but give me 10 minutes. What we will discuss should make this slide clear. So let us understand about this fork system call in some detail. So the fork system call does not take any arguments. And it has three different return types, return values, I mean. So suppose a particular process calls fork. So that means it is telling the kernel that I want to create a new process. Now the fork returns a value. If the fork returns a negative value, then the creation of a child process was unsuccessful for whatever reasons. Okay, we are not discussing in detail possible reasons, but let's say that in some kernels there is a limit to the number of new processes that one process can create. Right, there is a limit to the number of new processes that one process can create. So if maybe this process is trying to create too many processes, then at some point fork may return a negative value. Okay, so this provision is there so that fork can indicate back to the process that a child could not be created. So then fork returns a negative value. But suppose that the creation of a child process was successful. Then fork has a strange behavior. This is one function which returns twice. Once it returns to the parent process, which called fork, and another time it returns to the child process, the newly created child process. And there is a distinction between these two returns. Fork returns a 0 to the newly created child process. So fork returns with 0. And while returning to the parent process, fork returns a positive value, which is the process ID of the child process. So fork is a strange function in that way that it returns twice. Once it returns to the parent process, so fork returns once in the parent process. When it does so, it returns the process ID of the newly created child, which is non-zero, because there can be no process with a 0 or a negative process ID. Secondly, fork also returns in the child process, because now remember these are two different processes, parent and child. So fork also returns in the child process with a return value of 0. So let's again understand this part. As I said, if the call to fork is executed successfully, the kernel will make an identical copy of the parent's address space for use by the child. So initially you had only this one process in memory. It has its own code, its data, its stack, heap, etc. Now the kernel, since fork has been called and it has executed successfully, creates an exact duplicate of the address space of this parent. So this becomes the child. So now the child also has exactly the same code, the same data, the same stack, heap, etc. So at this point, the child is an exact duplicate of the parent. Also, just like if you understand, there should be some mechanism to remember which is the next instruction to be executed. There's some concept like the value of the program counter, etc. Right? That is also copied. So at this point, just after fork, say fork has completed. So now the kernel has made a different, separate, the kernel has created a separate child process, which is an exact copy of the parent. So the child's address space is an exact copy of the parent's address space, to the extent that since the program counter of the parent indicated that this is the next instruction which the parent should execute, that same information will be copied to the child also. So the child will also begin execution from the statement just after fork. So these are exact copies, parent and child. If the parent, so it's kind of natural, right? That once fork completes, the parent's execution should resume from this point, the statement just after fork. Similarly for child also, the execution will start from this line, which is just after fork. Okay, so there are exact two copies, exact the same copies, duplicate copy. Now, you might think, what is the use at all, right? So I create a new process, but I cannot make it do anything new. It will do the same thing as the parent. Truly, that's not a very practical approach. Therefore, Linux or Unix gives us at least two ways to make a child do something different than the parent. Let us discuss those two ways. So see here we show a picture where the parent is the same as the child. The code is the same. Okay, this is the code you have written. This was running as the parent process. For the child also, the same code will run, right? Because as I said, the child has the same text segment as the parent. Therefore, the code of the child is the same as that of the parent. Okay. Now, interesting thing to note here is, so the parent has executed this PID equal to fork. And suppose fork has been successful. So now remember that fork will return once in the parent and once in the child. So now look at the next few statements. If PID equal to 0, then a function child process is called, else parent process function is called. Right, so the code remains the same in both parent and child, but now they will start behaving differently. Why? Because we discussed a couple of slides back, fork will return differently to the parent and the child. To the parent, the fork will return the PID of the child, which in this example is a 3456. Okay, so let's say the parent has a PID of, say, let's say 3450. It created a new child and the kernel assigned the PID 3456 to that child. So fork will return 3456 to the parent process, right? So what will the parent, right? How will the parent execute after this fork call? To come here and see if PID equal to 0. No, PID is not 0. PID is the return value for fork, which is 3456. Therefore, the parent will go to this else part and will execute parent process. But what happens in the child? Fork returns with a value of 0. So now PID equal to 0. So the child will come to this next step and find this to be true if PID equal to 0. And therefore, it will execute the child process. So now you see you can separate out or differentiate between what the parent does and the child does. Whatever you want the parent to do, you write inside this parent process. And whatever you want the child to do, you write within this child process. Okay. So this is one way of separating out parent and the child. Also, there is another way. A second way of making a child do something different than the parent. That is the system call known as exec. And exec has several variants. The function of exec is this. It replaces the calling process. That means the process which calls exec with another program. So understand carefully. A particular process has called exec. So what will happen? Calling process will be terminated. And okay, I should not say here the calling process will be terminated, but let's try to understand what is going on. The codes, the address space, right? So this process continues, but with a completely new set of instructions or a completely new program. So while calling exec, you have to specify a executable code, right? And executable code can mean, any exe or something similar in Linux. For example, it can be the ./a.out or a.out file that you have created using compiler on a C program. So that kind of an executable file you will have to indicate along with exec. So exec takes as argument some such executable file, and that specified file, that specified program will be loaded in the same address space as the calling process. Okay. So if a particular process calls exec, it is as good as, like practically, that this process will no longer run. This process will no longer run. Rather, if you have said that, okay, let me give a concrete example, that it would be simpler. So exec, say you specify here exec with the executable code of ls. Ls is a standard shell utility which lists the current directory, and it has its binary executable, like something like /bin/ls. Right, so ls has its executable or the executable version. So while calling exec, you can actually specify ls. So then what will happen? The program that you are running for all practical purposes will be terminated. So that program will no longer run. Rather, the specified program, that means in our case ls, the executable of that will be loaded in the same address space and then executed. So now this process will no longer run according to the code you had written. since you had called exec ls, it will now run like with the code of ls. Right? So this is another way of making a child do something different than the parent. I'll just explain this part with an example. Right. So yeah, and yeah, the new process image has the same process ID, same file descriptors, etc. Now, one thing I'm leaving as a homework, there are several variants of exec. Things like exec L, exec LE, exec LP, exec V, exec VE, exec VP. There are usually these 6 variants of exec. Learn what is the difference between these 6 versions. You will see that the differences are mainly in what other arguments you can send to exec. You have to send one executable file as argument, things like ls. But then in some cases you will be able to send some, command line arguments to that program which you want to be executed. Or in other cases you might even send a defined environment, etc. So just look up these. So there are these several versions of or variants of exec. They all have the same functionality, as in they replace the address space of the calling program or the calling process with the some other program. So that part is the same, but there is some difference. There are some differences in what the different variants of exec take as arguments. So please study them. Now let me just describe these calls. We can join them into, or we can, we will study a complete example which will make it clear what we are talking about. Now, suppose the parent has created a child. So the child can do exactly the same as what the parent is doing. The code can be the same, or we have discussed 2 different ways by which a child can do something different. The child can exec, etc. But let's say that the parent wants to wait for a child to complete. So the operating system gives us this kind of a facility that a parent process can indicate to the kernel that it wants for a child to complete. And this is done using the wait system call. So what happens? So suppose a parent has forked a child, or it has forked multiple children. Then it calls wait. So what happens? The parent execution is suspended. Right. So again, this is an example of the parent process voluntarily saying that I do not want to execute unless one of my children complete or one of my children is terminated. So here, as if the parent it voluntarily gives up the CPU, the control over the CPU. So now parent execution is suspended. And it will become ready only after child terminates. So that is what the parent process has indicated. I want to wait for a terminate or complete. So now this parent process is no longer ready. It is kind of suspended or waiting for an event, which is completion of a child. This parent process will become ready only after the child terminates. Now there is one special case here. Suppose the parent created the child and immediately after creating the child, the parent was swapped out or the parent was deallocated from the CPU. Some other processes ran, the child also ran, and let's say the child completed. Before the parent could execute the wait system call. Okay, so understand again what I'm saying. The parent executed a fork system call and a child was created. So now there are 2 processes, parent and child. For some reason, the parent was deallocated from the CPU immediately after this fork, which can happen. A timer interrupt can come, etc., etc. So at this point, the parent has created a child. The child is an independent process. Now at this point, there is no guarantee that which one will execute first or which one will be allocated the CPU first. Will it be the child or will it be the parent? It may happen that the child was allocated the CPU first. The parent is still like in the ready queue. It can happen. And let's say the child finished its execution before the parent was again allocated the CPU. So now the parent is allocated the CPU and it executes a wait system call. Okay. So what does the OS find? That the child has already terminated. Then the parent will not be made to wait. Rather, this call to wait returns immediately. Otherwise, if that child has not terminated yet, this wait call will block the parent process until a child terminates. So I think you know what are blocking and non-blocking calls. Right. So if not, just look up these two terms. A blocking call is where the execution of a process is temporarily suspended until that function returns. That's a blocking function call. And a non-blocking call is the call returns immediately. So here, this wait is an intelligent kind of function. If the child has already terminated, then the call returns immediately. Otherwise, the wait system call blocks until a child terminates. And there are wait system call has two variants of its own. One is just wait. It suspends execution of the current process until one of its children terminates. Okay. So suppose a particular process has created several children. So calling wait will suspend execution of the current process until any one of its child terminates. There is another version called wait PID, where you specify a particular PID. So by this PID, you are designating one particular child. So you are saying suspend execution of this current process until the child specified by PID terminates. Right, so here with wait, we are waiting for any child to terminate. Right, whereas with wait PID, you are waiting for a particular child to terminate. And which particular child? The one that you designate using PID. Now, before giving some examples, this is the last thing that we need to discuss. Process termination. This is simple. A child process is terminated, or any process is terminated when it executes the last statement. Also, the kernel gives a exit system call for deleting the process. So what happens when a process calls exit? It returns status data to the parent via wait. If any parent is waiting for the termination of this process, and deallocate the resources that are held by this process. Now, okay. So this is exit. This is simple. Let me once check how much time the class has. Okay, maybe 10 minutes left. Okay. Yeah, perfect time to give some examples. So we have discussed several operations. One was creating a process, fork. Second was exec, by which a process can be replaced by another process. Then we discussed wait, by which a process can wait for its child to complete. And finally, we have discussed exit. Right. So now let's look at some examples which will kind of connect these system calls. First example is this. So this is the parent, this is the child. Let's say the parent has created the child using fork, etc. That part is not shown here. But then the parent calls wait. So when calling wait, you need to pass the address of an integer to wait. It takes as argument the address of an integer. And this wait actually returns two things. Of course, a function cannot return two things. That is why we use this pointer. So basically, wait has to inform the parent two things. First, the PID of the child that terminated. Okay, so wait, since the process called wait, it wants to wait for any of these children to terminate. Right. So when wait returns, it tells the parent which child terminated, and that is done using PID. Also, the child here, while doing exit, it can send a code back. So exit 2. You must have many times written exit 0 or exit 1. So this is a code which the child wants to send back to its parent. So that value is filled in status. Okay. That value is filled in status. Again, wait wants to inform the parent two things. There is no way in C by which a function can return two things. Therefore, one information is returned, which is the process ID of the child that was terminated. The second is the status code with which that child exited. Now, the status code has several implications. For example, if you write the child process in that way, you might use exit 0 to indicate that everything was OK, or exit 1 to indicate a particular error had occurred, or exit 2 to indicate some other error had occurred, and so on. The usual convention is you exit with code 0 or status 0 if everything went according to expectations, but you exit with 1 or exit with 2, etc., some non-zero value to indicate different error conditions. But whatever be it, this mechanism will inform the parent that which child terminated and with what status in exit. Okay. So this is an example which shows the relationship between wait and exit. Now let us show a full example. So I'll end this class with this example. So this is a complete example which uses fork, exec, wait, everything. Okay. So see, first of all, you have to include this header file unistd.h, and also sometimes systypes.h. So systypes defines various data types which are used by the kernel, like PID_T. I think this type is typedef in systypes.h. I don't fully remember whether it is in systypes.h or unistd.h. That you can check, but I think it's in systypes.h. This definition of or declaration of this type called PIDT. So here what does main do? PIDT PID, right? Then it forks a child process. So PID equal to fork. And then comes the type of, the type of code that we have seen earlier. See, if PID less than 0, else if PID equal to 0, else. So if PID is less than 0, that means fork returns with less than 0. That means fork failed. Okay, so you return 1. This is an error condition. Else, at least fork was successful. So now we need to distinguish between parent and child. So see, else if PID equal to 0. So as we discussed, fork will return with 0 in the child. So if PID equal to 0 means this is the child process. So here you see exec LP is called. So exec LP is a variant of exec. I told you to study the different variants. And see here ls is being invoked. Right, so /bin/ls is a executable of the ls program that is being invoked here. So now the child here will execute ls. The child will no longer execute this code which you are seeing. It will execute ls. Okay. Else, which is the parent process. So the parent will wait for the child to complete. So see, it has called wait null. Here it has created just one child. So by definition, it is waiting for that child. But yes, if it had created multiple children, then also wait would be waiting for all of them and would come back. The process would resume when any one of the children terminated. But here we have only one child. So basically this wait call will block, assuming that the child has not yet completed. And this, control will come back to this parent process only when the child has terminated. So then it prints child complete and then it ends. Okay, so this is a complete example which links fork, exec, wait, and so on. And the previous example in the previous slide showed us the relationship between wait and exit. Fine. So I'll stop here today. Please go through this recording. If you have any questions in the next live class, which will be on Thursday, we'll give you sufficient time to discuss the questions. Okay. Thanks everyone.